Before I tell you something about dimension analysis, pi factors and so on, I want to talk about some basic concepts. In physics, people distinguish between three things: quantity, dimension, and unit. Let's take a look at the following table for some examples. So here we have the quantity, here the dimension, and this here is the unit. So the first quantity is small l, which describes a length. Its dimension is denoted with a capital L. So the dimension is capital L. The unit is meter. Meter. The next quantity is small t, which describes time. The dimension of t is denoted with capital T. The unit of a time is seconds, small s. The next quantity is mass. Dimension of a mass is denoted with a capital M. And the unit of a mass is kilogram. Now something more difficult. The velocity v. Its dimension is L times t to the power of -1. So L times t to the power of -1. The unit is meter per second. Maybe you have already heard something about the 7 SI basic units. The first three examples, meter, second, and kilogram, describe such basic units. It is possible to write any other physical unit as a combination of the 7 basic units, like in the last example, where the unit of V is a combination of the first 2 basic units, meter and second, because the unit of V is meters per second, which is a combination of the first 2 basic units. Now that we know about these basic concepts, I will show you how you can calculate pi factors and how to use them to derive physical formulas. So let's assume you want to find a formula for the cycle duration t of a mathematical pendulum. So we want to find the cycle duration t of such a pendulum. So t is the duration it takes the pendulum to go all the way here and then back to the starting position. And we want to find the time it takes the pendulum to go all the way here and then back to the starting position. Also, we do not consider any air drag. This is why this pendulum is called mathematical pendulum. The first thing we have to do is to think about all the physical quantities that could affect the duration t. So t, in our example, could be some function of the mass m, the length of the rope L, and the gravitational constant g. Right now, this is just an assumption. We just assume the formula of T depends on M, L, and G. Now we will write all these quantities M, L, and G together with T in a table, like that. So we have T, M, L, and G. Next, we need the dimension of these quantities here. So we need the dimension of T, which is capital T to the power of 1. We need the dimension of the mass, which is capital M to the power of 1. We need the dimension of the length of the rope, which is capital L to the power of 1, and we need the dimension of the gravitational constant g, which is L to the power of 1 times t to the power of minus 2, because g is an acceleration. On the left of the table here, we write the basic dimensions these quantities t, m, l, and g depend on. So we need t, capital T, capital M, and capital L, because the dimension of g only depends on L and T. So it's enough to consider capital T, M, and L. Now let's take a look at these exponents here. 1, 1, 1, 1, and minus 2. They tell us how often a basic dimension appears in the dimension of a quantity. We will write these numbers here in this table here. So the quantity t only depends on the basic dimension capital T, and this to the power of 1. So 1 times capital T, no mass and no length. The quantity m only depends on the mass capital M, and this to the power of 1. So no time, no length, and mass gets a 1. So the length L only depends on capital L, and this to the power of 1. So L1, no mass and no time. The gravitational constant G depends on L and this to the power of 1. So L gets a 1 and it depends on T to the power of -2. So T minus 2, and it doesn't depend on capital M. So 0. Now we have this matrix here. Let's call it A. We want to find out the rank of this matrix A. You can use any approach you want to calculate the rank. For example, you could use the elimination approach. In this case, it is easy to see that the matrix A is of rank 3 because of the first 3 columns of this matrix. Next, you have to pick 3 linear independent columns of the matrix A, because the matrix A is of rank 3. It doesn't matter which ones you pick. You have the freedom of choice, as long as the columns are linear independent. Also note that your choice will affect the pi factors you get, so it could happen that different choices lead to different results. In our example, we will pick the first 3 columns. So this one, that one, and that one. The first 3 columns are obviously linear independent. Now we have to write the remaining columns in our example, the column with G, so -2, 0, and 1, as a linear combination of the 3 picked columns. So this column, that column, and that column. So -2, 0, and 1, which is this column here, should be a linear combination of these 3 columns. We want to find the values A1, A2, and A3. It is easy to see that A1 has to be -2, A2 has to be 0, and A3 is equal to 1. Now you can write down the pi factor pi1. The first thing you have to write down is the quantity that corresponds to the column you just wrote down as a linear combination. So this column was written down as a linear combination, and the corresponding quantity is G. So you write down G times, and then you add the quantities that correspond to the columns you picked earlier. So you picked these 3 columns, so you have to add T times M times L. Next, you have to add these 3 values, -2, 0, and 1, as exponents to these quantities. So T gets the exponent -2, m 0, and L 1. The last thing you have to do is to change the signs of these exponents. So -2 becomes +2, 0 doesn't have a sign, and 1 becomes -1. Let's check the dimension of the pi factor pi1. So the dimension of pi1 is equal to the dimension of g times the dimension of t, small t, to the power of 2 times the dimension of L, small l, to the power of -1. So this is equal to, so the dimension of g is capital L times t to the power of -2. The dimension of t to the power of 2 is t squared, capital T squared, and the dimension of small l is capital L to the power of -1. And this here is equal to 1. So this means the pi factor pi1 doesn't have a dimension, so it's dimensionless. This should always be the case. So every pi factor you calculate should be dimensionless. To get the formula for t from the pi factor pi1, we need a theorem, the so-called Pi-Theorem. The Pi-Theorem states that we can write one pi factor pi1 as some function of the other factors. So if pi1 to pi k are the pi factors, then pi1 is equal to r of pi2 to pi k, where r is some function. A special case is k is equal to 1. This means that there is only one pi factor pi1. Then pi1 is equal to c, where c is some constant. So in our example, we only have one pi factor. So this is the special case here. So we know from the Pi-Theorem that there is some constant, so that pi1 is equal to c. So the Pi-Theorem leads us to pi1 is equal to g times t squared times L to the power of -1, and this is equal to c. This last part is the Pi-Theorem. And now we can finally solve for t. So from this here we get t squared is equal to, so when we get this here and that here on this side, this leads to c times L times g to the power of -1. Now we can take the square root and get t is equal to the square root of c times the square root of L times g to the power of -1. And the last thing we can do is to rename this constant square root of c into the constant d. So we just call this constant here the square root of c d. Then this is equal to d times the square root of L times g to the power of -1. So dimension analysis leads to this formula for t. The constant d can only be approximated. You have to do a real experiment using a real pendulum with a given length L. Measure the duration t and plug t, L and g in this formula, and then you can calculate or approximate the constant d. So with dimension analysis alone you can't find this value d. You have to do an experiment to approximate the value d. If you want to find the exact value for the constant d, you have to solve, for example, the pendulum differential equation. By the way, the exact value for d is 2 pi. But as I said, you can't find this value with dimension analysis alone. One last note. I told you at this point here that you can choose any 3 linear independent columns of this matrix here. Let's see what happens when we pick different columns. So instead of picking these columns, we, for example, pick these columns here. The column with M, the column with L, and the column with G. So these columns are linear independent, so we can pick them. Then we have to write the remaining column, this time the column with T, as a linear combination of these picked columns here. So let's change this so it fits. So this time we have to write the column with t as a linear combination. So 1, 0, 0 has to be a1 times okay, 0, 1, 0, 0, 0, 1, and minus 2, 0, 1. So the t column has to be a linear combination of these three columns here. And when we solve this equation system here, we get a1 has to be 0. So a1 has to be 0. a2 is 1 half. And a3 is minus 1 half. For the pi factor pi1, we get t times, so then the values that correspond to the columns you picked earlier, so m times l times g. Then we add these values here as exponents, so here 0, here 1 half, and here minus 1 half, and then we change the signs, so minus 1 half plus 1 half. This time this here is the pi factor pi1. So to get a formula for t, we will use the Pi-Theorem. So let's change this here to that here. Okay, and now we can solve for t and get t is equal to c times g to the power of minus 1 half times l to the power of 1 half, and this is equal to c times the square root of l times g to the power of -1. So this here is the same formula we got when using the first 3 columns. So this approach leads to the same formula for t, which is a good thing. The next video will be a summary of the results of this video. I will show you step for step how you can calculate pi factors in a more general way.